you're like trying to pull your hairs, like, right? There's no information. You're operating on lack of information, right? Because I didn't explicitly tell you this in this class. I did it in the other one. 70 GPA is what? Glass? Okay. And glass is what class of material? Ceramics. Okay. And what about aluminum? What kind of class of material is that? Aluminum. Is it a polymer, metal, or is it a ceramic? Here, this is aluminum right here. See this? This is aluminum. What is it? It's a metal. Okay. What is the elastic modulus of aluminum? Too high? 200, just like steel? Okay, see, it's all relative. Okay, so what? Take a wild guess. 30, was it 30? You think it's lower than glass? 130. Okay. Anybody else? Take a wild guess. It's the same as glass, 70 gigapascals. So that's all I want you to know. Why? Because when you're going to see something that's 3,000 gigapascals, or you're going to see something that's, it's very easy to make a mistake if there's no physical understanding. So you can imagine some student would use 20 gigapascals instead of 200 gigapascals, and you're off by 10. And then when you actually make the part, it's going to fail because of that. Okay. I heard a very interesting analogy because I watched this documentary. There's a famous case where a lawyer used ChatGPT and got in trouble because the cases that were cited did not exist. I don't know, they lost their license, but you don't want to get embarrassed. But the idea is that at this point, AI is like a fresh out from college that remembers everything. Can you imagine that? So this is the power. It has access to all of the textbooks. It has access to all of the knowledge that humanity generated so far. Okay? It just doesn't have that much experience as a fresh out. So that's where the human comes in, and you are the human. You are going to be responsible for BS if there's going to be some BS. Does that make any sense? Okay. Let's continue with this because we're kind of behind in this one. We talked about the weight percent and the atomic percent. And we talked about volume percent, right? And there's a difference, right? Did you do any homework problems or practice problems during the help session related to this? Does everybody understand the difference? Yes? Huh? But it included the Avogadro's number, but it didn't have this. Okay. So again, for the weight percent, it's the mass of the components. For the atomic percent, it's the number of moles of one component. And how many are there atoms in one mole? 10 to the 23. Okay, and then you have the atomic mass, which is written where? In the periodic table. Okay, so things are easy if they're easy, and they don't have to be hard, and that's what I'm trying to do. Okay. Line defects, dislocations are one-dimensional defects around each where atoms are misaligned. And there are two types of dislocations. There's a edge dislocation and there's a screw dislocation. Am I going to get popular on TikTok? All right. Screw dislocation and edge dislocation. And believe it or not, dislocations were predicted by the mathematicians. And the idea is that to have some kind of transport, I'll have this analogy of either a worm or a caterpillar. Have you ever seen a caterpillar move? It moves portion of its body. And what I want you to imagine is, you see here's carpet. I love carpet because it hides dirt. And I hate carpet because it's filthy. But anyway, imagine that there's a new crew that came down to lay down carpet. Okay? And they roll it out, and it is a couple of inches long on one side here, and it's a couple of inches short on the other side. How would you go about moving it? Pull it. How many guys is it going to take to pull a piece of carpet this big? What if it's the size of the room? Okay. What you could do is you could shake it and propagate a wave that will travel, or you could go like this, and move it one step at a time, and eventually it's going to do that. So if I want to, when was the last time you have been to a movie theater or a concert? I was talking to a friend of mine. We want to go to Gypsy Kings in Eckerd Hall. They're coming Valentine's Day, February 14th. I already bought the tickets. He wanted the tickets close to the exit, and I wanted the tickets close to the center because I'm going to film short videos of Gypsy Kings and put it on TikTok and analyze some statistics about TikTok. And I want to be in the center. He wants to be in the end, right? And it's your perfect personal preference where you want to sit in this room, right? If you want your seat, you come a little early. But if I want to, I'm coming with Coke and popcorn. I'm coming over here, and that's my seat over there. So you can imagine that popcorn goes everywhere, and the soda and all that. What is the more energetically way for me to occupy a seat? If you move to that seat, then you can move to her seat, and you can move to that seat, and then I occupy this seat, right? Now, if I'm a very little tiny guy, like a kid, it would be easier for me to just walk in and occupy that spot, right? Doesn't make any sense? All right, so what we do is, imagine a deck of cards. And a deck of cards, a magician or you just shear like this, right? So that's what we're doing. This lattice, which is single crystal, is being sheared. And as a result, there is extra half a plane of atoms that is here, that's moving. And it is energetically favorable to do it this way, and this is called edge dislocation. So there are two planes associated. There's half a plane of atoms right here, and this is called the slid plane. So what's the analogy? I mean, have you ever been skating? You can go to the mall, and there's a skating ring, and you can skate. You have the skis, it's slippery. So imagine this is the skating ring. This plane here is the skating ring, and this is the skater that just moves in that plane. And it's called edge dislocation. The other type is a screw dislocation, and the screw dislocation is shown over here. So instead of moving this whole thing, it's moved one at a time, like this. So this is the motion of one atomic spacing at a time. Okay? Now, I need to tell you what a Burgers vector is. You like burgers? That's not the one. That's not why it has the name, Burgers vector. But the Burgers vector is determined by what's called a Burgers circuit. and around the dislocation you start to count the atoms, and at a certain point you're going to be one short, so then you have to complete that circuit. You just do the counting, right? So in the end, this Burgers vector is going to translate to some kind of interplanar spacing within that crystal, okay? And we're going to express it in terms of the lattice parameter A and stuff like that. But there's a separate letter that's used for the Burgers vector B. And you can see that for the edge dislocation, the Burgers vector is perpendicular to the dislocation line. For the screw dislocation, this Burgers vector is parallel to the dislocation line, and this is the top view, if you look from the top. And in reality, most of the dislocations are mixed. So there is a screw and an edge dislocation. You see here's an edge dislocation, and here's a screw dislocation. All of the plastic deformation of metals, like we took a paper clip and we were bending it, is resolved by the generation and motion of dislocations. And these dislocations happen in a single crystal, and for the polycrystalline material, it's one grain. So in that grain, that's how the plastic deformation happens. What's your feel about this so far? How many of you have used VMSC, Virtual Material Science? Here you go, dislocations. Edge. So we started to shear this crystal at a certain point. And as a result, here is this extra half a plane of atoms. You see this? It's highlighted in yellow. You see it? Okay. So we pushed it. We sheared it in this direction. So please remember this. Plastic deformation only happens by shear. Okay? So shear. We're inducing shear. And then this extra half a plane is going to move, and eventually it can come out on the other side. So it is a dynamic process. It takes time for the dislocation to move. Kind of like a car, right? You can go slow, you can go fast. And here's the screw dislocation. You can see here how it comes over here. And it's not the whole lattice that's being sheared, unlike an edge. Like if this were to come out over here, that would be an edge dislocation that started on one side and exited on the other side. So this is the screw dislocation. And here's a mixed. So here we have a screw, and here we have an edge. You can see that it is here in between the two positions. So that's extra half a plane. It is, for the notation, the dislocations are identified like an inverse letter T. You see this? And sometimes, like if there's more than one, it will be this inverse T and S, dislocations, more than one. How do we observe them? Like this. This is a scale of 200 microns. 200 microns is roughly just a little over your hair diameter. Okay? And what you see here is maybe this is nichrome alloy, and this lines over here are different kinds of dislocations. And if you do this under the microscope and you apply the shear stress, you can see them move, you can see them multiply. My analogy to this dislocation business is traffic, okay? If there are a lot of cars on the road, they tend to move slower. You would agree? Okay. So, what is the materials classes about? To control the process, to control the structure, to control the properties. Okay, there's always a balance between making things hard versus soft. If we make things hard, they tend to be more brittle. We make things softer, they are becoming more ductile. And plastic deformation only happens by shear. So it doesn't matter if you're taking the deck of cards and you're doing this, or you're doing this, like kind of like twist thing. So that twist thing, that's your screw, and this one would be your edge, where you go like that. Does that make any sense? Okay. You can watch movies online of the dislocations, generation in motion. If we take a single crystal and we subject it to uniaxial tension, then after plastic deformation, we can see certain steps that would originate on the surface, and those steps consist of thousands and thousands of dislocations. Do you guys realize that the slides are online? Okay, just want to make sure. Not hiding anything. So after plastic deformation, they're called persistent slip bands. They emerge at the surface at a certain angle. Okay? And how does plastic deformation happen? By shear. Very good. Okay. So how do we get shear? If we are applying just something and we put it in tension. A force has a projection. Force is a vector, right? Okay. So if you look at this chair, right here, if I apply the force like this, I'm pushing on this chair, but if I move this force and to a certain angle, then this force that I'm applying is going to have horizontal component, correct? Okay. So what happens here, as you can see, is that this force is going to have a projection onto this plane, correct? Right? You can use trigonometry to calculate how much that projection is going to be, and that is how one kind of loading results in another kind of loading. So even if you take something and put it in uniaxial tension, you're generating shear on certain planes. The difference between mechanics of solids and material science, this class, is that we're actually linking this to physical crystallographic planes in the crystal. Another type of defect are called twins. And here's the lattice. This is the twin boundary. And then it's basically kind of like a mirror image of the lattice. So this is called the twin plane. Like you can see that A prime is the same as A and C is the same as C prime. And, this happens. A mirror image of the lattice. Another type of planar defect, of interfacial defect, is a stacking fold. And a stacking fold for FCC, we determined that it is going to be ABC, ABC. And here, there could be an arrangement where this would be ABC, AB, ABC. And that is an example of a stacking fold in the structure. Um, here's a single crystal of cerium zirconium oxide. And you can see this is the scale bar of 5 nanometers. Whenever you present anything, you need to put a micron bar. Because how many times did it happen to you when you look at something online, you've never seen the object in the physical world, and you buy it and it's not what you expected, size-wise? You know what I'm talking about? All right. So back in the day, we started in terms of magnification. Say, okay, this is 20,000x, or this is 1,000x, or however many x. And the problem now is that it made sense when things were printed in a book, because that way, the sizing part mattered. Now everything is more or less digital, and you need to place what's called a micron bar or a ruler. Like if you want to sell something, you put a ruler right next to this object to kind of say this is the relative size of this, or this could be the size of this room. That's very important. Okay, going back to this catalytic converter, this is using surface defects to oxidize CO to CO2, and every car by law in the United States has this catalytic converter. These are the steps. There's a kink, and there's a step, and the terrace, and the vacancies. And this catalytic converters provide the surface for this process to happen. The difference between the catalytic reaction is that the catalyst typically is not consumed. So you can continue this process. In other words, you can just continue to oxidize CO to CO2 in your catalytic converter in your car. Okay, what is this class is about? To control the process, to control the structure, to control the properties. How do we look at structure? There has to be some sort of a microscope. Okay, and also material science is always about some sort of a length scale. How big is big? Or what are we looking at? And the main parameter is the grain size. And why is that an important parameter, would you think? What kind of structure does the grain have? Is it a crystal? Typically, is it a single crystal? Yes. So polycrystalline materials consist of grains, and every grain is a single crystal. And in that crystal, there are certain crystallographic directions, so when that dislocation moves, it moves to the end. And once it reaches the end, it cannot move anymore. I wish I could go through this one. It's a good feeling. But I can't. All right? Now, it doesn't really happen like this. There's not a wall. There's a different direction. So if I want to walk this way, I'm walking this way, and then I make a turn. And every time I make a turn, I have to slow down. Because if not, because of inertia, I'm going to hit that wall, which I don't want to do. This is why they put those roundabouts when you're driving, to slow down and control the 40s. What is it, 40? To get off 42nd Street has a whole bunch of those roundabouts going to Hillsborough. Yeah, they don't have to put the stop sign, and it's a more efficient way to control the traffic. And again, the analogy is nature. Okay, so this grain size can vary from material to material, and it can be very large. Like if it is a single crystal, the whole single crystal is one grain, if you think about it, like diamond. Or it could be very small, or it could be in the nanometer scale. So we need some sort of a device to magnify. And optical microscopy could go up to 2000x magnification, roughly. And it's using a visible light. What is the wavelength of visible light? Roughly. Anybody had a laser pointer? Play with a cat? Yes? No? No cats? Who has a cat? Nobody has a cat? Anybody has a dog? Okay. Interesting. The laser pointer has the wavelength, like the red one would be however many nanometers, and the green one, I brought one in here. It was like, what, 532 nanometers or something like that? So what's the wavelength of visible light, give or take? Okay. What is it? 400 to 700 nanometers is the wavelength of the visible light. So would you say it's close to a micron? Would you say that it is close to a micron? How many nanometers in a micron? What? It's 1,000, okay, 1,000 nanometers in a micron. So the wavelength, we have this for X-rays. If you want to look at something, the wavelength of the radiation has to be comparable to what you're looking at. Why is it called blue ray? Do you even know do you know what a CD is? What is CD? What does CD stand for? I mean, at a bank, it's a certificate of deposit, but for a physical device, it's called compact disc. Okay, and then there was a next step up after that, a DVD. And what is the DVD standing for? What is it? Can you look it up? Tell us. And then there was a Blu-ray. And what's the difference between all these devices? It was the wavelength of the laser that is, so Blu-ray is a blue laser. Okay, so the density of, and how does it work recording the data on those CD, which is DVD and a Blu-ray? You have any idea? See, this is a problem because everything is streamed from Netflix. Right? You don't need a Blu-ray these days. But are they still around?
Still
Sure they are. Anybody use the Blu-ray? You have a Blu-ray burner. What do you use the Blu-ray for?
Just sometimes watch random shows or watch the news.
Okay. All right.
Well, my
Wavelength. Do you remember when we talked about grains? We talked about grain boundaries. And I think it was right here. So I can just go back. Right here. You see this grain boundary? What did I tell you before? What does it say here? High chemical reactivity. So when you etch it, when you take this microstructure and you put it in acid, what it does, it etches the grain boundaries at a higher rate than the grains themselves. And as a result, you have something that's not flat. So you have grooves like this. And optical microscopy is very sensitive to the height in Z down to the wavelength of light down to 1 micron. Okay? And how many of you have ever looked in the optical microscope? You looked in the optical microscope? Where did that happen? Your job. What were you doing at your job? Aerospace parts. Okay. Did that microscope have a fixed objective lens, or you could rotate the objective lenses? So, what kind of objective lenses are typically there on an optical microscope? Because they're marked. Do you remember what that objective lens was marked? It said a number and then X. You know what I mean? How big were big? How did it magnify it quite a bit? Okay, so here you can see this is 3/4 of a millimeter. Very small, which definitely you cannot see with your naked eye, which is why under the microscope, this is brass, which is a copper zinc alloy, and you can see the grains. So here's an example of iron chromium alloy, and you can see the grain boundaries. Okay, there's ASTM grain size, and the formula for that is N is equal 2 to the power of G minus 1. Okay, and N is the number of grains per square inch at 100x magnification. Now, my background was in metals processing and material science, but nobody ever explained to me. And I learned this in graduate school when I had access to expensive equipment like scanning electron microscope or and an optical microscope. I had features I had to look at, just like you had to look at the parts, right, to do some critical measurements of some sort, right? And the SEM, which we'll discuss next, gives you a ruler. It tells you how big is the size. And then I realized that whatever I'm measuring, because there's an optical ruler, and you need to calibrate your optical microscope, like when you put something in there, like this is a centimeter, and you look at it and you say, okay, this is a centimeter. So you calibrate it. You take a picture of this, and you say, okay, this is a centimeter. I can calibrate it just like a ruler, but just like you would measure something with a ruler. Or calipers, you would do the same measurements, but at a very, very small scale. So what I learned is that I was off by a factor of 10. Okay? And the reason I was off by a factor of 10 is because if you ever look at the optical microscope, pull a picture of an optical microscope. Say optical microscope picture. It has two objective lenses. It has one lens that actually looking at your sample with a stage where you position it, fun part, where you can move it, the sample around. And then you have an eyepiece, or you have a digital camera that's in the eyepiece, okay? And that objective lens on the bottom that's right next to the sample has a mark. And typically it says 5x, 10x, 20x, 50x, 100x, 200x. Okay? But if you look at the eyepiece, you would look at the marking, and it would say 10x typically, or it would be variable for an expensive microscope. Are you looking at a picture of a microscope? You know what I'm talking about? There you go. Okay. So what happens is when you have an objective lens here on the bottom, and you have another objective lens over here, then your magnification, let's say if you have 50x here, and you have another 10x here, what's the magnification? Yes, it is 500. Okay, so typically when it says here at 100x, it would mean that on the bottom of your scope, it's a 10x objective lens most of the time. And it's a very common magnification. And at that scale, the working distance, the focal distance is large, so you're not going to jam the sample into the microscope, which happens all the time, and you ruin the lens. Because if you're not looking, because you have the control of there's a knob on the side, right? What this knob does, it moves the sample closer to the lens. So here's your lens, and what happens, and I've seen this happen too many times, is that you take your sample and you ram it into the optical objective, and it can be ruined this way. You don't want to do that. Okay? So 10x times another 10 gives you 100x magnification, and at this scale, this is the equation for the ASTM grain size number. which is 2 times G minus 1, where G is that ASTM grain size. So you're going to make some calculations about like grain size of different structures. The funny part is that you can tell this is an American thing, American Standard AS, and American Standard, because it's per square inch. So, in optical microscopy, we're using polarized light to increase the contrast. And how many of you have flown a plane? Yeah, anybody flew international? Overseas? No? Yes? Boeing? Airbus? You go to the lavatory, or close to the lavatory, there's this big, door. You can open it and get out if you want. No, don't do that. And even if you try to open it, it will not open. Does anybody know why? The pressure difference. Yeah, you won't be able to open it, but you'll get in trouble, so please don't do that. But if you look at the window, there's typically on that door, there's a little circular window, and it has a little thing that you can rotate. It's a polarizer. Anybody has glasses? Sunglasses? Polarizing sunglasses. What does that mean? Okay. I'm going to tell you if these are polarizing sunglasses or not by looking at the screen of my phone. And these are not polarizing sunglasses. Because if you have the polarizing sunglasses, then at a certain point you won't be able to see your phone. Have you ever experienced that? Okay, so at least I'm ringing some bells here. So if you are polarizing the light, so the light passes through the polarizing filter, and then you can increase the resolution and the sharpness of it. And there's sometimes a polarizer and an analyzer, which are films that polarize the light, and if they're off phase, like everything is going to be completely dark, and if they are aligned, there's going to be white, so you can adjust the intensity of this light without adjusting the voltage on the bulb, whatever the bulb is. Okay, for electron microscopy, the electrons have high resolution on the order of the wavelength of about 100 nanometers, and the resolution is, optical scopes, the best resolution you can get is comparable to the wavelength. So you just told me 300 to 700 nanometers. I mean, there's some massaging techniques that you can try, and the price of the scope goes from $200 to $20,000. But bottom line is that you're not going to be getting anything better than 0.1 micron, which is 100 nanometers. Can we use X-rays? Possibly, but X-rays are very hard to focus. But we can use electron beams. The electron beam could have the wavelength of like 3 picometers, so the resolution is 0.003 nanometers possible, or up to 1 million. And when I worked at Motorola, we had a Hitachi scope that had a magnification of 1 million. And a good electron microscope is $500,000 to start, and could go up to $1 million. It's expensive piece of equipment. We have Nano Research Center at USF, and we have a couple of scopes there, just in case you wanted to know. So we can attain atomic resolution, and the electron beam is focused by the magnetic lenses instead of the optical lenses. There's also scanning tunneling microscopy. You can see carbon monoxide molecules that are arranged to show a human, or this is a Chinese character for atom, and this was done by manipulation. These are individual atoms that form that. So the way scanning tunneling microscopy works is that there's a cantilever, and this cantilever is compliant, and there's a laser that shines at that cantilever, and it goes into the detector. And then if you drag that cantilever over the surface, this cantilever is interacting with the individual atoms of the surface, similar to that potential that I showed you, that potential well that you made the calculations. And that's how, if you have positioning of your surface down to using a piezo, typically. This atomic force microscopy was invented at NIST, National Institute of Standards and Technology. You can get resolution. It's so fun, and you got to be very patient to work with microscopes because it takes time, and you have to worry about drift, and just takes patience. You can get the best microscopist I've ever worked with is Larry Rice at Motorola. He just had a AA degree, and he was the microscopist from God. He just had a AA degree. Didn't have a bachelor's degree, but he did great. It's a special skill. You have to have good hands, sensitive hands. You need to know your instrument. It's not just like driving a car, which how many of you like sports driving? You really need to know what you're doing when you're racing or something in the car, the full control of the car. It's a similar thing, but except that you're not controlling the car, you're controlling the microscope down to the atomic resolution. Okay, we talked about defects, point defects, linear defects, and interfacial defects. I introduced the equation that gives you the number of defects that you can calculate at every temperature, and I showed you a whooping hard, easy manipulation that Nate Goldstein did and ended up at Air Force by taking natural values of both sides of this equation. And we talked about dislocations, which are edge, screw, and mixed. Okay. All right, let's talk about diffusion. We'll start. Diffusion. How can you define diffusion? Diffusion. Have you done an experiment in physics when you were in school where you take some water and you take some dye and you put a drop of dye in water? Yes? No? Rings the bell? Right? And then eventually, over time, in an hour, in a day, in a week, this dye and water mix, and you have the blend of color, and it's continuous color throughout. Okay, that's the process called diffusion. And in gases and liquids, it happens by the Brownian motion, or random motion. The biggest difference between diffusion in solid state and Brownian motion is that you have to occupy the seat of some sort. So we're going to talk about mechanisms that deal with diffusion and examples, and how it is used for metals processing, and also the equations to solve it, and how that rate depends on temperature. So we're going to have some exponents as well. So to define it to you legally, it's called the transport of mass by atomic motion. So atoms physically move to have this process. And as I already stated, in gases and liquids, it's by Brownian motion. And in solids, it's by vacancy and interstitial diffusion. Interdiffusion is the diffusion of atoms of one material into another. That's why it's called inter. Self-diffusion is the atomic migration in a pure metal, because atoms of the same species of the same type of atom can move N. This is material A, and this is material B. And this is the concentration of the material A versus position, and this is the concentration of the material B. Have you done this experiment in physics where you've taken two rods made of lead, scrape it with a knife, put them together, and they bond? No? Well, imagine an experiment where you take lead, which is super toxic, the teacher handles that in gloves, and they scrape the surface from the oxide, and they take two rods of lead and go like this, and they physically bond. Like you can let go, and it's going to be like this. Very simple experiment. I don't know why they don't do it in school here. Maybe because lead is toxic. So what is the process of this bonding? How does it bond? And why? There's no glue. This bonding happens by interdiffusion of lead into lead. And then what we did an experiment where we just take these two rods and we put some dead weights to determine how much load it's going to take to separate them. Okay, so initially there's a very large concentration gradient. Over time, obviously you hear two different types of atoms that are interdiffusing. So if we look at the concentration gradient over time, that's what it looks like. Does that make any sense? If we label these atoms as A, B, C, and D, after this process of diffusion, they may end up somewhere else. So those are the four locations. Before diffusion, these are the same atoms after diffusion. So they physically move. Those atoms move in the lattice. The mechanism of the diffusion, I called it 15. Have you ever seen this puzzle, or maybe played this puzzle, where there's a square and there are 15 smaller squares that you can move and put a puzzle together, a picture? What is it called? What's the name of it? Well, in other countries it's called 15. Why? The game is called 15. Huh? Why is it called 15? Because there are 15 squares, and the 16th is empty. So you can move to form a puzzle, to put it back together, one spot at a time. Okay? So for the diffusion to happen, there has to be an empty seat. So here's a vacancy. And if I want to occupy your seat, or if I want to have any transport, I mean, at the end of the class, you're just going to stand up and go, right? But you're not going to be able to leave as fast as those guys. That's why my friend wants to go and sit at the end, so he can come in first and leave first. Does that make sense? Okay. So here's a vacancy. And as a result of this vacancy, this vacuum, or this atom can occupy this vacancy by moving over here. Okay? Or this atom can move over here, or this atom can move over here. This means that both the atom moves, or atoms move, and the vacancy move, or vacancies move. Does that make any sense? Okay, so here's a vacancy. If you move over here, that vacancy is taken, and you left a vacancy where you were sitting. And this is how this diffusion process is done versus liquid or a gas, because there's many different, there are no specific seats, you know. It's like at a rock concert in a fan zone. Good luck. Does that make any sense? All right, so there's going to be a number of vacancies that we're going to use that equation, the exponential dependence that we introduced in the previous lecture. And there's going to be activation energy for the exchange, because you're going to have to pay some energetic cost to move from here to here. There's going to be an energy expense associated with that. And then this obviously happens in time. It doesn't happen instantaneously. This was a vacancy diffusion mechanism. There's another mechanism of diffusion called interstitial diffusion. And for interstitial diffusion, if I have some small objects that can fit, I can put this thing over here. And then it can move over there, and it can move anywhere. If I put a little dog, maybe, cat, or this object right here, which fits in between the seats. Do you see the difference? For a human, a student, it takes a space to occupy. Okay? But for a smaller atom, it can fit in each interatomic spacings. Right? So what was the best packing that we had for a closed pack structure? 74%. Okay? If you put a smaller atom in there, like carbon and iron, it will go as interstitial. And what is the definition of an interstitial? It's the space between those atoms. So, vacancy diffusion is much more rigid than interstitial diffusion, because there are many possibilities for interstitial diffusion. And this is a result of that. It happens much faster than vacancy diffusion. Case hardening is the process where we can take a gear of a car or a truck or any kind of mechanism, and we can make the skin much harder. You see this? There's even different colors. This is darker than this. As a result, we are improving the mechanical properties of the surface. It becomes more wear resistant, and it becomes harder. So this is case hardening for steel. And this is the diffusion of carbon atoms from the surface to this surface layer. And we can control the process, to control the structure, to control the properties. What do we need to know for something like this? We need to know the temperature at which we need to do case hardening. And the second parameter, we need to know the time, temperature and time. How long is it going to take to form a certain thickness of the skin layer to improve the properties of the gear? Also, we can induce compressive stress, and that would improve the fatigue life. The semiconductor devices, the computers, the cell phones, the whole 9 yards, is also controlled by diffusion. If you ever go to any semiconductor manufacturing plant, Intel, AMD, NVIDIA, Motorola, did I say Intel? They have what's called a diffusion bay. A diffusion bay where they do diffusion. And through the mask, you can put in phosphorus-rich layers, and when we talk about semiconductors and we heat it up, and this phosphorus is going to diffuse into silicon, making the different types of semiconductors by the process called doping. Doping, yes. Screw dislocation and the doping. I mean, I have to have a popular class, right? The diffusion of very small concentrations of atoms of impurity, in this case phosphorus, into the semiconductor silicon. And silicon is a semiconductor, so we can make it an insulator, or we can make it an apple. We can make it an apple. We can make it a conductor, a metal. We can make it a metal, that is going to conduct electricity. And through the gate, we can control whether it's going to be non-conducting or conducting, and that is going to correspond to a 1 and a 0 in a digital state. Okay. The rate of diffusion, because it's a time-dependent process, is determined by J, which is called the flux, and it is the mass of diffuse species over the area over time. So it has the dimensions of kilograms per square meter per second. And then we can measure this experimentally, how much of the stuff physically transports through a membrane, like a thin sheet, when we impose the concentration gradient across that sheet. So J is equal to M divided by AT, T is the time, or it's equal to I over A dm dt, dm dt, where M is the mass of the diffuse species versus time, and if we plot our data, then J becomes the slope. Before we stop, I want to just tell you that there are two types of diffusion. There's steady state diffusion and non-steady state diffusion. The driving force for diffusion is the concentration gradient. And if you've ever ridden a bicycle and you hit a nail, what happens? You have a flat tire. Yes? Anybody experienced that? You never experienced a flat tire on a bike?
I have a flat tire in my car.
Not like this. On your car. That's dangerous. Bicycle is also dangerous. My point is this. There's higher pressure in the tire. So initially, how about this? How many of you have taken the, what is it called? The centerpiece out to deflate the tire really fast? That's what I'm talking about. You didn't have to make a hole, but let's take that process, for example, right? It goes, so initially, the pressure difference is very, very high. But in the end, it becomes the same. The pressure inside the tire becomes equal to the air pressure. Is there still air in that tire that's deflated? Yes? Yes, but it's not leaving the tire because the concentration gradient, which is the pressure gradient, is gone. So, this is opposite to another problem where you have a membrane and you supply the pressure of a gas, and that gas goes through the membrane. So a famous problem in this class is when you take a paint stripper, which is a nasty chemical, and you have a glove, a latex glove, and you put some of that nasty chemical. The concentration of that chemical is so high that it can actually diffuse through the latex glove and cause harm. This is the reason why when you're dealing with something like this, you need special gloves to deal with that, right? So there are two types of diffusion, steady state and non-steady state. And that's what we're going to talk about on Thursday.
Quick question. Well, can I ask you?